Here's a second type of problem that we have, which is an AtWiz machine. As you can see, we've got all the information here. And again, if you want to get a printout of this, you can click on the link in the description or go to our notes page, and I've got a link both to this video and to the printout there as well. So again, I want to walk through this with you, giving you another opportunity to see the steps that need to be made so you are ready for this when it comes to the test that's coming up. So we've got the AtWiz machine. We've got block 1 has 430 grams, block 2 has 200 grams. I'm going to switch to the next slide here so I've got enough room to go ahead and start drawing and doing my equations. So remember, the way to tackle these problems is basically, you've got to know the steps. You've got to know the first, second, third steps to take. The first step that we usually do, there's really one of two. You can either determine what direction this is going to go, or you can draw your forces that are working on the systems, or on the system. So based on the information that's given to me, I know that block 1 has a mass of 430 grams, which is 0.43 kilograms, and block 2 has a mass of 200 kilograms, which is 0.2 kilograms. Based on that information, I can see that it would logically make sense that I would have a motion like this, where the block 1 will be going downward. So I'm going to make my positive direction in that way, saying that block 1 is going to be falling in that direction. So when I set up my net force equations, I got to keep that in mind. Now, other information given to me in the paragraph or drawing on the last slide, they tell me that there's a frictional torque acting in this pulley, and that's between the axle and the pulley itself. So that's 0.08 Newton meter. And then we have the radius, which is 5 centimeters or 0.05 meters. We got to watch our units. And our mass is 30 grams, which is 0.03 kilograms. So we've got that information on our pulley. So now that I've got all the information transferred, let's go ahead and do our forces. I'm going to have a tension force, I'll call that T1, acting on the 430 gram mass. I also have gravity acting on that mass. On mass 2, I've got a tension force going up, call that T2, and I've got a gravitational force going down. All right, so those are the two forces, or the net forces diagrams, acting on my two masses. Now I've got the pulley itself. Now the pulley is undergoing a torque, right? And that torque is being caused by this tension force pulling down, which is equal in magnitude to the T1. And then I've got this tension force pulling down this direction, right? We're going to call that T2. So now, next step, once we have all of the forces diagrammed, I'm going to go and start looking at my equations. And remember, this is where we start to isolate our objects and taking a look at the net force or the net torque, whichever is appropriate for that object. So here are my three objects. I'll try to color code them here to keep us straight as we go through and create our equations there. Oops. Right, I'm going to start with block 1, right, the net force, F net 1. I take a look at that, and I've got M1G, or the gravitational force of block 1 pulling down. All right, but that's in our positive direction, again, referencing our direction that we first came up with. That's in the positive direction. And then I've got the tension force, T1, pulling up. Now, generally what we're going to do is we're going to end with our pulley. And you can see in our pulley diagram, we've got those tensions there. So we're going to want to go ahead and solve these equations for the tension. So I've got T1 is equal to M1G, right, minus F net. But remember, F net is, by Newton's second law, ma. So that simplifies into that, right? And that's our net force equation rearranged to solve for the tension of our first object. Our second object, right, we're going to do is we're going to do our mass 2 down on the bottom there, right? Look at that. So I've got F net 2 is equal to, now T2 is going in the positive direction because that's going up and over there, minus M2G, or the gravitational force on mass 2. So again, wanting to rearrange for those tensions, knowing that I'm going to need them in my equation for my pulley there, will be, again, F net is ma, according to Newton's second law, plus M2G. So that gives me my net force equation for that second mass. And then we go to the pulley. Now the pulley is undergoing, like we said before, a torque. So we want that torque then, right, that net torque equation for the pulley. Now, what's causing torques on that pulley? Well, we've got T1 acting on the left-hand side. That's pulling it in the positive direction. And now remember, torque is your force, which in this case is T1, or the tension 1, times the radius, right? The radius in this case is going to be this r, the 0.05, and I'm going to leave it in variable form for right now. So that's my tension, or sorry, my torque because of tension 1. And then tension 2 over on the right-hand side, that's causing a counterclockwise torque. So that's going to be negative T2, again, multiplied force times the radius at which it's being applied. And now this problem has friction, right? Has a frictional torque. So that's going to slow the acceleration. It's going to slow the motion of this system down. So it's going to be a minus sign there. And the quantity is 0.08 Newton meters. Okay, so that's how you incorporate the frictional torque. Now, if there was no torque, or sorry, no frictional torque, no friction in the system, then you just leave that minus 0.08 out, which is what we've done in the past sometimes. So, but we've got it in there, so we're going to keep it in there for this time. Now, if you remember from previous lectures, we know that torque is also equal to the moment of inertia times the angular acceleration, or I times alpha, right? And that's going to equal, again, I'll write all this down, T1R minus T2R minus 0.08. All right, and then this is a disk. This is a pulley. So it has, unless otherwise stated, we say that it acts like a disk. And a disk has a moment of inertia of 1/2 mr squared. Right? And we are looking for, if you look back at the question, it's asking you what's the acceleration. Now that's the linear acceleration, not the angular acceleration. So we make our substitution. We know that angular acceleration is equal to the linear acceleration divided by the radius. So we make that substitution there. Right? And that's equal to, again, T1R minus T2R minus, wow, this thing's really acting up today, minus our frictional torque. All right, now if we take a look at our problem, we can do a little simplification here. I've got an r there that's going to cancel with the squared in our moment of inertia. And if you look, we've got a r in this term, and r in this term, and an r in this term, but no r in the last term. So if we want to try to make it a little simpler, what we can do is we can cancel these. We can't forget that if we're going to do that, we have to do it to this term as well. We have to divide by that r in that term. So if I simplify that and get rid of all my marks there, that's going to leave me with 1/2 times my mass times the acceleration is equal to tension 1 minus tension 2 minus 0.08 divided by r. Right? So that, right, ends up being my final net torque equation. Now from there on out, as I've mentioned in the past, as we've gone through these in class, that just basically leaves algebra. So let's go ahead and do the substitutions and finish the algebra. Get the acceleration of the system now. So that's the acceleration of each one of the blocks, the linear acceleration of each one of the blocks is going to be 1.01 meters per second squared. Now, with that information, we can go back and we can solve for the second question that they're asking for, which is the tension of the pulleys, right? Just by going ahead and plugging it into our tension equations. We get that the first tension is 3.78 newtons. Then we can plug in for our second tension. And that tension is 2.162 newtons. Okay, so those steps, again, no matter what problem you have, if it's a torque problem like this, an Atwood's machine problem, if you've got a modified Atwood's with a object on a surface, or if it's just as the next problem will be just one mass, it's the same steps. You do your net torque equation, your net force equation for each one of the masses. You do the net torque equation for the pulley or the rotating object. Solve for the acceleration. Maybe they give you the acceleration. The first steps are still the same. You have to get those net torque equations and the net force equations. Otherwise, you won't have enough information to solve for anything else. So Hope this helps. So you can apply these to some of the problems in the packet or some of the WebAssign problems, and I hope it helps you work through those.